Hey everyone, welcome to our third episode in Multi-Agent Reinforcement Learning. Today we are diving into one of the most fascinating and challenging aspects of MARL, learning dynamics, which I like to call the evolutionary game. As you can see from the title, we are not just talking about the algorithms today, we are talking about a dance of intelligence, the constant evolution that happens when multiple learning agents interact with each other. This is where MARL becomes truly different from single agent reinforcement learning. And now let me start with an analogy that captures the essence of what we are studying today. Think about the difference between a solo performance and a group dance. In single agent learning, our agent is like a solo performer on a steady stage. The word doesn't change, it's predictable and reliable. The agent can perfect one routine, master the steps, and achieve optimal performance. But in multi-agent learning, that's entirely different. It's like a group dance where every dancer's move changes the entire choreography. When one dancer spins left and everyone must adapt, and when another changes the tempo, the whole rhythm shifts. So the goal isn't just to perfect your own moves, it's to learn how to adapt and coordinate in real time. And so this is the fundamental challenge we face in MARL. How do you learn when the very act of learning changes the world around you? So today we are going to learn the choreography of this dance and dynamics that govern how multiple agents learn and evolve together. Before we jump into today's material, let's quickly recap what we've been and map out where we are going. In our previous lessons, we explored the fundamental architectures that define how agents can be organized, like CTCE, CTDE, and DTDE. Now think of these as the blueprints of our multi-agent systems. But blueprints are just static plans. And today we're going to see how these agents actually evolve and learn over time. And our mission today has three main objectives. First one, we'll explore self-play, the art of creating the perfect sparring agents. How do you build an opponent that makes you stronger rather than just easier to beat it? Okay. Second, we'll dive into policy gradient, the mathematics of social influence. When your success depends on others' actions, how do you calculate what to learn? And third, we'll tackle mean field theory, our solution for taming the chaos when you have hundreds or thousands of agents interacting simultaneously. And plus, we'll have a live demonstration to see these concepts in action. Now let's get to the heart of the matter. Here's the central challenge that makes MARL so uniquely difficult. For any single agent's perspective, the environment is a moving target. Look at this diagram. So agent A is trying to learn optimal behavior, but agent B's action constantly change what optimal means. And meanwhile, agent B faces the exact same problem with agent A. So it's like trying to hit a target that moves every time you adjust your aim. And the target moves because other people are also trying to hit their own moving targets. So this creates what I call learning on shifting sands. The ground truth keeps changing beneath your feet. And in single agent RL, you can eventually converge to an optimal policy because the environment is stationary. But here, the very notion of optimal is in constant flux. So this brings us to our billion-dollar question. How do we achieve stable learning when the correct answer is always changing? So the three techniques we'll cover today each offer a different approach to this fundamental challenge. Okay? Now let's start with our first approach, self-play, or as I like to call it, fighting against your shadow. Okay? To understand why self-play is necessary, let's consider what happens when we train against fixed opponents. Now imagine you are training a chess AI, and your opponent always uses the same beginner's 4-move checkmate strategy. Now what happens? Initially, your AI struggles and loses frequently, but gradually it learns to recognize this specific pattern. It learns the exactly counter moves. Eventually, it becomes absolutely brilliant at defending against this one attack. Your AI now has 1% win rate and is the world champion of defending the 4-mover checkmate. The reward signal is fantastic because you win every game. Okay, but here's the problem. Your AI has become brittle because it's overfit to one specific opponent. So imagine put it against the other strategy, a different opening, a more complex attack, and even basic tactical variations. Maybe it will fail miserably. Okay, so this is what I call the Red Queen's fallacy, borrowed from the Alice in Wonderland. The Red Queen told Alice, "You can run faster and faster, but you are not actually getting anywhere." In our case, you can get higher and higher rewards, but you are not actually getting smarter if your opponent is standing still. Okay, so what's the solution? What if your opponent was always a slightly better version of yourself? So this is the core insight behind self-play. It provides what we call an auto-curriculum, an automatically generated sequence of increasingly difficult training tasks. Here's why this works so brilliantly. Okay, the first one is continuous improvement. You can never rest on your laurels. To beat your opponent, you must constantly adapt and improve because your opponent is also you and also improving. So the second one is robustness. By playing against the diverse pool of your own past strategies, you build a policy that isn't easily exploited. You can't overfit to one strategy because you are constantly facing new variations of yourself. Okay? Then, emergent complexity. This is perhaps the most amazing part. Complex, sophisticated, even human-like strategies can emerge from this simple process of playing against yourself. You don't need to program strategy, it evolves naturally. Okay? Now let me show you how this works in practice with one of the most successful examples, AlphaStar's League training system. We have the main agents. It's the current best version of your AI, but it doesn't just train against one opponent. Instead, it trains against the entire league of the different players. Okay, including past version of itself, ensuring it doesn't forget old skills and exploiter agents. These are specifically trained to find and exploit weakness in the main agent and historical snapshots, preserving diverse strategies from different stages of training. So the exploiter agents are particularly clever. Their job isn't to be generally good at the game. It's to find a specific weakness in the main agent and exploit them ruthlessly. So this forces the main agent to constantly patch its weakness. So this creates a never-ending arms race where the agent must become increasingly robust and sophisticated to survive. Okay? Now self-play isn't just a clever engineering trick. It's actually an approximation of a powerful game theoretic algorithm called Policy Space Response Oracles, or PSRO. And here's how PSRO works. First, we need to start with initial policies. Your first set of strategies may be random or handcrafted. Okay, and then compute the best response. We need to, for each agent, we need to train a new policy that optimally responds to the current mix of opponent strategies. And then add to league. Incorporate this new best response policy into your training population. And then repeat. Go back to step 2 with your expanded league. And what does this achieve? This process iteratively builds a strategy set that converges towards a Nash equilibrium of the game. Remember, a Nash equilibrium is a state where no player can unilaterally improve their outcome by changing their strategies. Okay? And AlphaStar's League is essentially a practical, large-scale implementation of the theoretical framework. And it's taking the abstract mathematics of game theory and turning it into a concrete training algorithm. Okay, before we move on, let me ask you a quick question in chat. What do you think is the main advantage of self-play over training against a fixed opponent? Type A for better strategy, type B for faster training, or C for avoiding overfitting. Okay? Great. I think most of you may choose the C, avoid overfitting. That's exactly right. Self-play prevents the strategic brittleness we get from the fixed opponents, right? Okay, now let's move to our second major topic, policy gradient, or as I called it, the subtle art of social influence. Okay, in single agent reinforcement learning, the policy gradients are beautifully straightforward. The math is clean and intuitive. If an agent led to good outcome, then do it more often. Okay, we can read it as the gradient of our objective equals the expectation of the trajectories of the gradient of the log probability of our action, weighted by how good that action was, the advantage function. Okay, this works because the environment is stationary. Good actions today will be good actions tomorrow. But in multi-agent RL, everything changes. The outcome for agent I doesn't just depend on its own policy, but also everyone else's policies. So look at the gradient now. Okay, this gradient is contaminated by the choices of others. When agent I receives a reward, how much of that reward is due to its own smart action and how much is due to lack? Means being paired with helpful teammates or facing weak opponents. This is a credit assignment problem on steroids. And how can we assign credit or blame correctly when everything is interconnected? That's the question. So let's look at our first approach, independent learning, or as I call it, optimist. So this is exactly the independent learning. That's algorithm like IQL or IPPO. So this algorithm is principled on assumption. So let's try to imagine dancers trying to perfect their choreography, but each dancer practices in isolation, hoping everyone else does the same, and they can't see what other dancers are doing, but they assume everyone is improving at the same rate. So IQL and IPPO treat all other agents as a part of the static environment, and each agent calculates its gradient completely ignoring the fact that other agents' policies are also changing. So the mathematics become simple because each agent just does standard single agent RL and replicate it n times in parallel. Okay, suppose we are 10 agents, then we replicate the single agent RL for 10 times. Okay, so this is incredibly simple and scalable. You can take any single agent algorithm and instantly make it multi-agent by running multiple copies. But this severely violates the stationary assumption that underlies reinforcement learning theory. When all agents are simultaneously changing their policies, the environment becomes non-stationary from everyone's perspective. And this often leads to chaotic, unstable learning where agents never converge to good policies. Okay, the second approach is centralized critic, which I call the coordinator. And think of this as having a dance instructor who watches everyone during practice and gives personalized feedback to each dancer. And during rehearsal, the instructor can see the full picture and get each person. But during the actual performance, the dancer must perform independently, right? This follows the CTD paradigm we discussed in previous episode, right? During training, a centralized critic observes everyone's state and action simultaneously, and this allows it to learn an accurate cue function that captures the true value of the joint action. And each agent gets feedbacks based on this global perspective. And during execution, the critic is discarded, right? And each agent acts using only its local policy and local observation. So algorithms like MADDPG, COMMA, and MAPPO use this approach. The key insight is that having access to global information during training allows the critic to provide stable, informed gradients to each agent. And even though the agents themselves only act on local information, right? Okay, now let me show you the difference visually. With independent gradients, you may see the erratic, noisy trajectories, and the agent may circle around the equilibrium, overshoot it, or never converge at all. The learning is unstable because each agent's target keeps moving. Okay, with a centralized critic, you may get more smooth and stable convergence directly towards the equilibrium. The shared global information provides a stable learning signal that guides both agents towards mutually optimal policies. Okay, look at this picture. This picture is from the MADDPG paper. It shows that in the CC environment, this environment, okay, MADDPG successfully learns correct behavior. The speaker outputs the target landmark colors to the get listener, but DDPG struggles. The speaker repeats the same utterance while the listener moves to the middle for landmarks. Okay, and they impede this environment. MADDPG learns to cover both landmarks to confuse an adversary, and DDPG fails. One agent greedily pursues the green landmark followed by the adversary, while the other agent scatters. Okay, the key difference is MADDPG learns coordinated cooperation, while DDPG cannot handle multi-agent coordination due to the independent learning. This is why centralized critics have become the cornerstone of modern multi-agent reinforcement learning. Okay, quick poll time. Which approach do you think would work better for training autonomous cars to cooperate in intersections? So type 1 for independent learning, type 2 for centralized critics. I think most of you will choose centralized critics. You are absolutely right. Car coordination needs stable, predictable learning, which is exactly what centralized critics provide. Okay? Now let's tackle our final challenge. What happens when we have not just 2 or 3 agents, but hundreds or thousands? This brings us to main field theory, our method for going from individuals to population trends. Okay? So here's the fundamental scalability problem in MARL. The joint action space grows exponentially with the number of agents, right? Okay? So this is computationally intractable, right, when we have 100 of agents. You simply cannot model every possible combination of actions when you have large numbers of agents, okay? But here's the key insight. Do we really need to model every individual interaction? In many scenarios, let's think traffic, financial markets, swarm robotics, what matters isn't the specific behavior of individual agents, but the collective statistical behavior of the population. Okay? Can we approximate the effect of the crowd without modeling every single individual? Okay? Mean field theory says, instead of tracking every agent individually, track the behavior of the average agent is more soundable, right? The core assumption is beautifully simple. As the number of agents n approaches infinity, the influence of any single agent on another becomes very weak. So what matters is the collective average effect of population. Mathematically, we transform an n-player game into an unparalleled two-player game. Each individual agent plays not against n-1 specific other agents, but against the main field, the average policy of all other agents. So think of it as this. Instead of asking, how should I respond to Alice, Bob, Charlie, David, and other 996 other specific individuals, you may ask, how should I respond to the average behavior of I expect to see from the population? Okay, so this dramatically reduces the complexity while capturing the essential dynamics of the large-scale multi-agent interactions. Okay, now let me show you how this works mathematically. In standard MARL, the Q function for agent I depends on its own state and action, plus the states and actions of all other agents, right? But in main field Q-learning, we approximate this by taking the expectation of the average action from the main policy, okay? The payoff is enormous. The Q function for agent I now only depends on its own state action pair and the main policy of its neighbors. We've reduced the complexity from exponential to linear in the number of agents. So this approximation is remarkably accurate when the number of agents is large, because the law of large numbers ensures that the average behavior becomes predictable even when individual behavior is random. Okay? Now, final question. If we have 1,000 agents with 5 actions each, how many joint actions would standard MARL need to consider? Okay, I think type A for millions, type B for billions, type C for more than that. Okay, I think most of you will choose the C, more than that, because this is exactly why we need mean field theory. Okay. Now let me give you a concrete example: swarm robotics. The challenge is you want to coordinate thousands of simple drones or robots. Maybe they are searching for survivors after a disaster or mapping unknown territory. It's completely intractable to model every drone-to-drone interaction explicitly. And the main field solution is each drone doesn't need to know what every other specific drone is doing. Instead, it only needs to react to local population statistics, like the average movement direction in its vicinity, and the density of nearby drones, and the average speed of the swarm, right? For instance, a drone may learn if the local density is high, then spread out. If the every direction is north and I haven't seen anything interesting, then follow the trend. If the most nearby drones are moving slowly, they might find something. Investigate. Okay, this captures the essential coordination dynamics while being computationally tractable even for very large swarms. Okay. Here's another powerful application: modeling economic and traffic systems. The challenge is simulate a citywide traffic flow or financial market with millions of participants. The behavior of any single driver or trader is statistically insignificant, but the collective behavior creates the emergent patterns like traffic jams or market crashes. So the main field solution is for traffic, model how an individual driver reacts to average congestion level and average speed and average route choices, rather than tracking every single other car. Okay, and for economics, model how a trader reacts to the average market sentiment, whether the overall market is bullish or bearish, rather than tracking every individual trade. Okay, this approach has been successfully used to model anything from epidemic spread to social media dynamics. The key insight is that in large populations, individual differences often average out, leaving predictable microscopic patterns. Okay. Now let's see these concepts in action. Okay.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter.
You can open the corresponding link to watch the complete video. And now let's briefly summarize the content of this video in 3 aspects. The first one, self-play perspective. In the hide-and-seek environment, self-play drives the co-evolution of competing strategies between hiders and seekers, right? Through the iterative gameplay, agents discover emergent behaviors like tool use and ramp construction, right, and lead to an evolutionary arm race where each team continuously adapts to counter the opponent's latest strategies. And from the policy gradient perspective, the policy gradient algorithms enable hiders and seekers to optimize their respective objectives, which is maximizing hiding duration versus minimizing discovery time. This method handles the complex action spaces involving navigation, objective manipulation, and coordination, while adapting to the non-stationary environment created the opposing team involving strategy. Okay? And from the main field theory perspective, I think when scaling to large population of hiders and seekers, main field approximations may help model collective behaviors like swarm hiding patterns or distributed seeking strategies. This framework transforms the complex multi-agent interaction to tractable computations by representing the influence of many agents through aggregated statistics. So enabling the analysis of emergent group dynamics in hide-and-seek scenarios. Okay.
On Earth.
Now let's summarize what we've learned today from the 4 key takeaways. Okay. The first is learning dynamic in MARL are fundamentally different from learning in single agent RL. The environment is non-stationary, the target keeps moving, and the traditional convergence guarantees breakdown. Okay, and second, self-play. Self-play provides an elegant solution to the opponent modeling problem. By playing against the evolving versions of yourself, you create an outer curriculum that leads to robust, sophisticated strategies without human domain knowledge. Okay. Third, policy gradient requires spatial handling in multi-agent settings. Independent learning is simple but unstable. Centralized critics provide the stability we need by giving agents a shared global perspective during training. Okay. The fourth is main field theory. And main field theory is our key to scaling MARL to large populations. By focusing on population statistics rather than individual interactions, we can handle thousands of agents with linear rather than exponential complexity. So how to unifying them together? Adaptation. In MARL, the most successful approaches are those that explicitly acknowledge and adapt to the constantly changing nature of MA environment. Okay. In our next lesson, we'll explore how these learning dynamics play out in specific game theoretical scenarios. We'll dive deep into cooperation, competition, and see how the algorithms we discussed today perform in classic multi-agent challenges like the prisoner's dilemma, coordination games, and mixed motive scenarios. Okay, and thank you for your great participation today. Just keep thinking about this concept, and I will see you next time when we put the theory into practice with concrete game scenarios. Okay, thank you. Bye bye.